We are going to be looking at solving a system of linear equations. In this particular example, or in this particular method, we are going to be looking at the elimination method. Let us consider the following system of linear equations. Notice, first of all, that these two equations are written in standard form, where we have the x term followed by the y term equals a constant. One of our first steps in doing this is to write both equations in this form, where the x's are lined up, the y's are lined up, the equal signs are lined up, and the constant terms are lined up. In this particular example, if you look at it closely, you can see that the y term and the x term, the two y terms, let me try to get my pointer so that you can see this better. We can see that in this example that our two y terms here, let me get my pen written, our two y terms here are the same, except for one is a positive and one is a negative. Consequently, if we take these two equations and add them just the way they stand, you will get the following result. We get here then, if we add these, adding our x terms, 2x plus x is 3x, and looking at the y terms, we have that the y plus the negative y adds up to nothing, and 7 plus 2 is equal to 9. Continuing then, dividing both sides by 3, we have x equals 3. This is half of the answer we need. Remember that solutions to systems of linear equations in two variables will be an ordered pair if the solution is unique. Continuing now, we're going to back substitute the 3 for the x in either of the two equations. I've chosen the first equation, 2x plus y equals 7. When we back substitute 3 for x, we're going to have 2 times 3 plus the y is equal to 7. Notice that we've taken the 3 here, and again, I have to get my cursor. Here we go. I've taken the 3 and I've substituted it for this x, and this gives me the following. I get just the 2 times 3 plus y equals 7. 2 times 3 is 6. Subtracting 6, we get 1. And this then gives us our final answer, which is the ordered pair 3, 1. In some cases, it's necessary to multiply one of the equations to make a pair of coefficients to be the opposite. Sometimes we have to multiply 2, but in this case, we're going to just look at multiplying 1. When we look at this particular equation, or pair of equations, systems of equations, you can see that we have the x's lined up, the y's lined up, and the constant terms lined up. When we look at this, it would be really, really nice if this was a negative 2y instead of just a minus y. And so we can accomplish that by multiplying the second equation by 2. Let's proceed as follows. Here's the original system. We are not going to change the first equation, so I'm just going to rewrite the first equation because I want to keep everything nice and neat and lined up. But we are going to take the second equation and multiply each term by 2. When we do this, we're going to have 2 times x, 2 times the negative y, and 2 times the negative 4. This results in 2x minus 2y equals negative 8. Now we can see that the coefficients of our y terms are the opposite of each other. Consequently, when we add the two equations term by term, we are going to get the following. 6x equals negative 6. Notice the y terms dropped out. 4x plus 2x is 6x, and 2 plus a negative 8 is a negative 6. Dividing by 6 gives us our x term of negative 1, our x coordinate. This is half of our answer. Now we're going to take the negative 1 and we're going to back substitute. Okay? I've chosen the second of the two equations, x minus y equals negative 4, because this is the easier of the two equations to work with, in my opinion. Substituting negative 1 for the x, we have negative x minus y equals negative 4. Adding 1 to both sides, we get the opposite of y equals negative 3. Multiplying both sides by negative 1, we get y equals 3. This gives us our final solution of the ordered pair negative 1, 3. Here's one more example. If you consider this system of equations, you'll notice that it's a bit harder than the first two that we looked at. In this system, we look at the x terms and we see coefficients of 2 and 3. If we look at the y terms, we see coefficients of negative 4 and 7. We have to make a decision which pair we want to try to eliminate. Do we want to eliminate x's or do we want to eliminate y's? One way to make a decision is to, we need to eliminate a variable. We need to multiply each equation by a constant to get a pair of coefficients to be the opposite. It's not going to be as easy as before, but we're going to choose the one with a smaller least common multiple. If you look at the least common multiple of the x terms, the 3 and the 2, we have a 6. The least common multiple of the y terms, the 4 and the 7 is 28. Generally speaking, the one that's smallest is going to be easier to work with. So we are going to proceed as follows. I want to try to eliminate my x terms, and I'm going to get the coefficient of this x term to be 6 or negative 6, and this one here to be the opposite, negative 6 or 6. We're going to proceed by multiplying the first equation by negative 2, giving a x coefficient of negative 6x. Our y's then, negative 4 times negative 2 is going to be positive 8. Our constant term, 4 times negative 2 is negative 8. In the second equation, we're going to multiply everything by 3. 3 times 2x is 6x. 3 times 7y is 21y. And 3 times 22 is 66. Now notice that our x coefficients are opposites. Therefore, when I add these two equations, the x terms drop out and we get 29y equals 58. Dividing both sides by 29, we have y equals 2. We're half done, actually more than half. If we now back substitute into either of the first two equations, this is the first of the two equations, we're going to back substitute the 2 for the y. So we have 3x minus 4 times 2 equals 4. Multiplying 4 times 2, we have 8. Adding 8 to both sides, we get 3x equals 12. Dividing both sides by 3, we have x equals 4. And this gives us our final solution of the ordered pair for 2. This finishes this first discussion of using the elimination method to solve a system of linear equations.